Okay, good afternoon or good morning for some of you. My name is Lennart Stahl, and I will, together with Wayne DeCosa, do this webinar. We are going to discuss how you design heat pump systems to comply with ASHRAE Standard 15.2. We're going to focus on the 15.2 that is for residential, and then in a few months we're going to talk about do a similar thing for ASHRAE Standard 15 that is for non-residential. This is like a follow-up for what the webinar a week ago when we introduced the H-series mini split system. And now we're going to discuss a little further, more in detail, how this is going to be, can be designed to meet the standard 15.2. We have a Q&A session, so you can put in your questions in writing, and then we will try to have time for that afterwards to answer the questions. If we don't have time for that, we will follow up with obviously with those answers. So this is agenda on the black. It's the introduction, that's where we are right now. Then an overview of A12s, what they are, and the standard 15.2. And then how you apply the standard. And then examples. Wayne has some really good examples showing very applicable how you do this. And then takeaway at the end, a couple of slides about takeaway. Some of the questions we're going to answer, you can see here. I don't expect you to read all of them, but we have got questions the last 6 months or so, and we put them together in a document, and we're going to try to address all of these, even more actually. Two most important questions in my mind are the top. What is the maximum allowed refrigerant charge for a room according to 15.2? And then also, do I need leak detection always or not? That's the main questions we're going to focus on, but there are others that you can see there we're going to discuss as well. So another one we get is, what are A12 refrigerants? Well, that is an ASHRAE name or classification of the refrigerants. EPA issued this significant new alternatives policy, and they listed 6 refrigerants that can be used. All because they have to have a low enough GWP, global warming potential. It has to be below 700. 14A and many others we use today don't have that. They also need to have an ODP, ozone depletion potential of 0. On the right side, you can see the ASHRAE matrix of these, and in the middle there we have R32 and R454B, and also the other 4 I mentioned earlier. The 2 there stands for, and that's a classification, means it's mildly flammable. L means that it indicates that it has low burning velocity. As you can see, if you look at the bottom of that chart, it shows that it's lower toxicity than some others. It also have much lower flammability than, for example, propane and butane that you have at the top of that chart. Are they flammable? No, not really. They can flame if 4 conditions are met. First of all, they need to have a high enough minimum ignition energy, MIE. Means that cigarettes, toasters, electric heaters, and other household products will not ignite an A2L. They also need a high enough temperature of that ignition or that spark, and it needs to be more than 1190 degrees Fahrenheit for R32. 454B will ignite at a lower temperature, but it has to be really, really high temperature. Also, they also need a constant supply of oxygen and a certain concentration for, you can see there that for R32, it needs to be between 14 and 33% concentration. If it's more or less, it can't ignite, because then we don't have those four items that I listed there. We need to remember that A2L have a very slow flame speed. Flame speed is 0.15 miles per hour. Walking speed is typically 3 miles per hour. So you can walk 20 times faster than the flame can spread. If you Google how fast people crawl, the answer is going to be 0.3. So you can still crawl twice as fast as a flame can spread if it ignites, or if it becomes a flame. Another question, what are the A2Ls and why? Which one are you using and why? And that was addressed in a seminar a year ago, a webinar in February a year ago. but we picked R32 because it's very established and very important. It is a single component refrigerant, meaning that it can be charged in both liquid and gas phases. The other ones listed there, the other 5 are blends, which means that they are more difficult to handle, especially if you have a leak or if you need to reclaim or recycle it, because it's 2 components at least. So in the table there, we compare, obviously the GWP and the ODP has to be good enough, and green means it's better than 410A. That's what we comparing with now. Charge, you can see it's 88% only needed compared to 410A. So less charge is going to be needed than with R32 compared to 410A. Capacity, similar, 9% better capacity than 410A. It's very mature and proven. We have had it in US a few years and outside US more than 10 years. And at the bottom I listed again, easy to handle it. It's a single component, and that's going to be advantage for us, especially when it comes to handle it. So when do we start to use A2L refrigerants? Well, we started almost 3 months ago, January 1st this year, but there are exceptions. In US, the EPA have done several rulings, and they are saying that if you have a non-A2L, for example, 410A, below 65,000 BTUs per hour's capacity, it has to be manufactured and imported before January 1st, 2025. But it can be installed during 2025. So it has to be done, but then you have a year sell-through to install it. It's kind of similar, but a little delayed when it comes to bigger system, for example, BRF, above 65,000 BTUs per hour. They had to be manufactured by January 1st, 2026, and they can be installed either by the end of 26 or end of 27. So it's a sell-through of either 1 or 2 years. The difference is that it depends on when it's permitted. If it's permitted after 10/5/23, it has to be done during 26. If it's an older permitted before 10/5/23, it's another year sell-through. So it's an extended time there when that system could be installed. Another question that is kind of common is, can the old 410A systems, for example, be retrofitted with A2Ls? No, they cannot. Even though they're similar in many ways, it's not a drop-in replacement. It's another refrigerant in the system is going to impact capacity and efficiency and the reliability and a few others. So you cannot do a drop-in. But the EPA says that older systems, you can still continue to manufacture components that needs to be used for maintaining existing systems to the end of the lifetime of that system. At the bottom, you can see how they define a new or an old system also. 75% or more of the evaporators, then it's a new system, or 100% of the compressor racks, then it's considered a new system. So how do we address safety regarding these A2Ls? This is a summary slide that's kind of busy, but until 2021, it was 2 standards, Standard 15 and Standard 34. And they were actually more than 100 years old. Then 2022, this was redone by ASHRAE, major revision. They split up the 15.2. So then we have 15.2 as a separate standard, and that is for residential. And that's the one we're going to focus on today. So that's for 22. And then actually end of last year, they revised all these. It was 400 pages. They put in the addendas that are being issued constantly in the document. So then we're down to only 200 pages for those 3 together. But already now, the beginning of this year, there's 2 new addendas. And the addendas are typically clarifications, minor edits, can even be a bigger edit. But addendas will then, on a regular basis, be put back into the standard. We need to remember that these standards are application-based standards. They are not equipment design guides. So standard 15.2 says it applies to the direct refrigeration systems in residential applications. You can also see it talks about 1 and 2 family dwellings and townhouses, individual sleeping units, in the multifamily dwellings. You can kind of see they're talking about hotels there, condos. Standard 15 is very clear. It applies to everything that doesn't apply to 15.2. Very easy definition. If it doesn't apply to 15.2, you have to use standard 15. Standard 34 is basically all those refrigerants classifications. We can, in general, ignore standard 34. Another definition here is residential occupancy. They also elaborated on that and saying residential occupancy. You can see the list there: dormitories, hotels, multi-unit apartments, and private residences. So that's a definition for this standard 15 too. So to answer the question, can standard 15 be used? It can in some cases, but the way to look at these standards is that you have these three standards on the left there, it's those three, and that's a lot of pages. So then we took the good stuff from those standards. They're not really written to be used by designers, for example, or contractors. It's a lot of information in them, kind of spread out. So we took the interesting stuff, the heat pumps, the R32, and the indoor comfort, because that's what we are working with. That's what Fujitsu has. And then we put that in a document, a 20-page document, an application guide, that you're going to get the QR code at the end of the presentation, so you can go and download it from our site. The question we get, should the local codes or the ASHRAE standards be followed? That's a good one, because an ASHRAE standard in itself doesn't do much. It has to go into IMC, International Mechanical Code, or something similar, and thereafter it can go down to city and state code. And so it can take time for that to happen. It can take years in some cases. What we have seen, though, is for these standards that reflect R32, the process is faster. These standards, the ASHRAE standards, saying that if it's a conflict between the ASHRAE standard and the local code or adopted code shall take precedence. So that's important. They put themselves in the background ASHRAE. It's up to the local code to be used, of course. So how do you know what code to use? Well, you can go to this website, AHRI. You have the QR code if you want to go there. You can also take a note about it. But so I did that. I went to that website. I clicked on Texas. And then on the left, it's hard to see. I can see breakdown and links to, for example, Austin and Houston and other places where I can go in and see what the local code right now, right there. And this is something that's being updated on a regular basis. Can standard 15 be used for a residence? It can, but it shouldn't. At the end of the day, you can see the definitions there for the standard 15.2 and the standard 15. But at the end of the day, it's up to the local inspector, the AHJ, authority having jurisdiction, to make the decision. In general, it's easier to use standard 15.2. Standard 15, especially for residential or smaller buildings or systems, standard 15 is much trickier, much more comprehensive, because it covers so much else than that specific residential. So now we are getting closer to the really important question we saw earlier. What's the maximum allowed refrigerant charge for a room according to standard 15.2? Well, it depends on three things at least. The space, the volume of the room. I'm using dispersal volume. It doesn't have to be exactly the same as a room, but dispersal volume, that's the area multiplied with the height. Then it depends on whether it has circulation, that room or that space, or those rooms, and also if it has ventilation. It's more detailed discussion about that in the application guide that we have mentioned a couple of times already. So let's try to answer that question. We need to define here. We're going to work through a few definitions. Dispersal floor area, that's the smallest room floor area where refrigerant could leak into. If you have multi-zone systems, you need to look at the smaller, because that's where technically the whole system could leak into. Dispersal height, according to standard 15.2 for ducted systems, is the mean of the ceiling heights in the space. but you can never use anything more than 9 feet for any when you calculate that mean. For ductless systems, it says that dispersal height is the lowest point of the equipment delivering conditioned air, but it can't be less than 2 or more than 9. So that's the restriction. Air circulation is defined as circulate air in the spaces without any outside air. Ventilation is bringing in outside air to displace or dilute any refrigerant in the space. So that's one definition. We're going to take a little closer look at the ceiling height, for example. Can you use the space above a suspended ceiling? When you look at the room volume, it depends. If you see on the left there, we have a ducted supply and return for that ducted unit above the ceiling. Then we cannot use the space above that lay-in ceiling. Dispersal height goes up to that false ceiling. But if we open one of them, for example, the return into the ducted unit, then that is considered to be a duct, a part of the duct, open, and then we can use the whole dispersal height all the way up to the top of that room. However, cannot be more than 9 feet. Have to remember that, cannot be more than 9 feet. Another question we have got for years now and even now is, can you use door undercuts or transfer grills? And you cannot. Above that cat picture, that's the wording in the standard. Cannot use transfer grills or undercuts according to standard 15.2. So if you have a room, you can see at the top view of a room there with an indoor unit conditioning room A. Depending on what's going on in that oval, in the red oval, we could perhaps include the room volume for that room as well, if it's open, if it's connected. And connected spaces, according to standard 15.2, is that has to be on the same floor. Those two rooms has to be on the same floor. Has to be permanent opening, had to go all the way down to the floor, and it has to be intended for people to walk through, cannot have a door. So it's an open passageways, that the way they define it. So if it has a door, can't be used because doors can be closed. It could possibly be some wiggle room on that, but cannot have a door, and it has to be big enough for people to walk through. So that's standard 15.2. Standard 15 say that you can have that. You can have something they call natural opening. And I'm just going to explain the difference here, but we're focusing on standard 15.2. But as you can see on the figure there, in case 1, everything below 1 foot could be used. So we could have a big door undercut if you use standard 15. Typically, we don't do that, especially not in residential applications. And important is to pick one of the standards for your application, and you have to stick to it through the whole process. But you can see that a low opening could be used. An opening that is too high cannot be used. If it's above the 1 foot, nothing can be used, or if it's partially above, only the part below that 1 foot can be used. There is a kind of complicated way to calculate the size of that opening. You see the formula there, but in that application guide I already mentioned, there is a diagram. You can go in and get how the answer on how big that vent should be. That's for standard 15, but let's focus on standard 15.2. 15.2, question we see sometimes. Can ductless systems have separate considerations for determining dispersal height? And they do. We saw earlier, ducted system has to be the average, but can't be used more than 9 feet for the ceiling height. For ducted systems, it's the opening delivering condition there. What that really means is on the left there. You can see a couple of wall units and the floor unit. The dispersal height in that case is 2 feet. Even if that floor unit is sitting on the floor, blowing air right across the floor, you cannot go below 2 feet in dispersal height. If I instead in the middle there have 2 wall units, one is 7 feet up with a delivering opening and the other one is higher, I use my 7 feet because that's the lowest point where you get air. On the right, we have another really high unit sitting high up, 10 feet. Can't use 10 feet. We have to use 9 feet for that. Okay, we're still trying to answer the question. How much is allowed? We have talked about the application guide on the left. You can see in that one, it's down in detail. But then we issued a new application bulletin a couple of days ago, actually. We released it, and we're going to take a closer look at that one. You're going to get the QR code at the end of this presentation. So this is a table. I'm going to try to walk you through the table. This is for R32 according to 15.2. And in this case, I look at the floor area in the blue on the left, the column on the left. I hit 250. I pick 250. I go out the step to the right. I see at 2 feet without air circulation and without ventilation, which typically is residential. You have no air circulating. With the fan, you have no ventilation. 250 feet and 2 feet of not room height. The room is probably not 2 feet, that's kind of low, but it would be the dispersal height. Then you can have 3.7 pounds in that room. That is allowed. That's the M max according to ASHRAE 15.2. But 8 foot might be more reasonable. Again, 250. Then I go out a little further. I can have 14.8 pounds. That's more than typical mini split systems. So that's 8 foot without air circulation, without ventilation. We can go further out. We can see air circulation, 2 feet, still very low. That's 4.8. So you can see from 3.7 without air circulation to with air circulation, we get another pound on the maximum allowed. And the same works, of course, for 8 feet. We're going to go instead of 14.8. So air circulation gives us another 4 pounds or 5 pounds. So that is how the table is used. It goes down to 1,025 square feet. That's what where the standard stops. And there are jumps here. Obviously, you have to interpolate depending on if you have other room heights and other areas. I can show you how that would be done. Let's say we have 7 feet, room height 195 square foot, no air circulation or ventilation. I would go in the blue and I can take the lowest, closest lower value. So I can take 175, that's lower than 195, go in and say 10.8 for my 7 foot. I play it safe, I can have 10.8 pounds there. But I could also interpolate and see where that 195 would land using the 10.8 and 11.6. That gives me 11.44, so it's almost 11.6, a little less when I interpolate. But you know, if you take the closest lower value, you should be good. Same would have to be done if you have 7.5 foot. The same thing, I go in this case at 200 square feet, I go out to the right and I will land at 7 or 8 feet in those columns. So if I decide to play it safe, it's going to be 11.6. But if I want to interpolate, it's going to be right in between those two. 7.5 is right in between 7 and 8, and that would be 12.4. So then I had 12.4 pounds. So that's the way you would interpolate to kind of get the exact numbers that you're looking at. We have looked without ventilation so far. Let's say we have some ventilation then. Then the table can be used this way. In my little example, I have 8 foot and 250 square feet. I have air circulation and ventilation. Air circulation means I need to go out to the right of this in the reddish area. And I go to 250 square feet. I go to 19.1. That's 19.1 pounds for those 8 feet. And that's good, but then I have ventilation too. So there's a footnote where you can go in and add for ventilation. In my case, I had 100 CFM, allows me to add 3.6. So I have the total of 22.7 pounds. So those 100 CFM give me a margin of 3.6 pounds extra of the allowed refrigerant amount for that case. So now I hope we know how this works. The table, let's look at how you can use the table then. Wayne is going to give some really good examples of that in a few slides. But let's look at H-series factory charges. That is what you saw a week ago in that seminar. The factory charges for those systems is between 1.19 pounds and 6.63. The higher number there is for, I think it's 4 tons and multi-zone. That's the factory charge. The factory charge obviously has a limit in how long piping lengths you can have, but Wayne is going to discuss that also in a few slides. But this is telling me, when I take a look at this, I circled 6.7 pounds. It's telling me that a 100 square foot room, any of those H-series systems, keeping to the factory charge, can be installed in a 100 square foot room with a 7-foot dispersal height. And 100 square feet, that's a standard bedroom, a small bedroom, according to Google. So you're good, actually, if the dispersal height is 7 feet. If it's a little less, let's say it's 6 feet, then the room needs to be 125. And it continues down. If it's only 4 feet for some reason, that dispersal height, then the room needs to be 225. So that's a practical way to use this table. You can go in and see what's reasonable in my case. Another question we get is, do I need leak detection or not? You don't need it always, typically not, especially not for residential applications. But we're going to look through this table together. First, I want to do some definitions. MS is the refrigerant system charge, the total charge in the system as it is. Then we have something we called M-max, and that's the one we just found out in the previous tables. We looked at the M-max, what's maximum allowed for that space. Then we can introduce something called MREL. That is a releasable refrigerant charge if you have shut-off valves. Wayne is going to explain that, probably not in residential, but in other applications, you could put in automatic shut-off valves in the refrigerant circuit that in case of a leak would shut off a part of the circuit, so the whole refrigerant cannot leak out, only part of it. That is the definitions. But let's look at the first one, the first row in that table. If the system charge is less than 4 pounds, you don't need LDS. LDS are not needed below 4 pounds. Next one, if the system charge, or we have that MREL, we have put in shut-off valves, it still has to be below 35. It can never be above 35, either of those two. And of course, the system charge or the MREL cannot be higher than the M-max that we calculated earlier. So above 35, it doesn't comply with standard 15.2. In the third row, we can see that if MREL is bigger than 4 or almost any number, and we put in the LDS, because that could be needed to operate the shut-off valves if we have that. The last one is above those 4 pounds. And let's say we want to operate air circulation in case of a leak, or ventilation in case of a leak. We need to sense the leak, and that would be done with the LDS. So that's actually a long way to describe the answer on the question. It's typically not needed, except in these extreme cases that listed here. So to summarize that slide in the bottom, charge above 4 pounds doesn't mean that LDS is required. Adding LDS doesn't really guarantee compliance. M-max is going to tell whether you are compliant or not. Okay, when it is your turn to give some examples how this information can be used.
Excellent. Thank you so much, Leonard. That's a lot of information, isn't it? That's really good. Oh, Leonard, you want to share your screen again? It went away. There we go. Okay.
Sorry.
Good. Oh, no worries. No worries. So I want to mention also, thank you for your questions so far. Just as a quick recap on questions, feel free to drop a question in the chat and we will do our best to answer them at the end of the presentation. So as I mentioned, it's a lot of information. And when you think about trying to comply with these new standards, it's kind of a game changer for our industry. And it's also a process. So I was just thinking about this while Leonard was talking. What are some other big things that we've encountered in recent years? When we went, for example, from R22 to R410A, that kind of shook up our world, didn't it? Same thing when we went to inverter-driven systems. That was a significant change. But, you know, like anything else, with some patience, perseverance, a positive attitude, a cooperative spirit, asking a lot of questions, and I don't mean from social media. Beware of some social media platforms. I've seen some comments that talk about shake your head. So, you know, my point is that we can get through this. And I really do that with, especially with repetition, you're going to understand these terms. And when you put it into a practical application, what I'm going to do here, I think hopefully the light goes off and you say, you know what, it's not as bad as I thought. So I picked an arbitrary example here of a 1,400 square foot home. So some givens here are, we've got a XLTH multi-zone system, 3-ton, R32. The factory charge, which I have, is listed as MS because it's the total system charge, unless you exceed a certain amount of piping, right, with the multi-zone system. So the factory charge in this is 5 pounds, 8 ounces. Now I did throw up some units here for tentative zone selections. And the reason I did that is, we'll talk about that in a minute. But if you look at the bottom paragraph, an excerpt from standard 15.2, and the reason I'm selecting here to put into an example of a multi-zone system is, this is going to be about as hard as it gets. If you can understand this, you'll have no problem with the single zone systems. So this is a worst case scenario where, as Leonard mentioned, you could have a larger capacity unit that could potentially release its entire refrigerant charge into the smallest zone. So the standard requires that the dispersal volume for each indoor unit shall be, which is not a suggestion, shall be calculated. And the smallest shall be, again, not a suggestion, shall be the dispersal volume used to compare against the maximum refrigerant charge. So what does all that mean? So of the 3 zones here, so the key variable that we're going to be looking at is volume, not just square footage, but as Leonard talked about, the dispersal height. So dispersal height for a floor mount unit may only be 2 feet, for example. So that's going to significantly affect your volume. So we have 3 zones here. So the zone on the lower right, which consists of a bedroom and a bath. Now you can see that there's a partition there. So technically those are not connected spaces, but they are if we have a ducted unit, because a ducted unit will take the aggregate of all the areas in the same zone. So in this case, we have 284 square feet. So keep that in mind on the lower right. Zone 2, 284 square feet. That's got a dispersal height of 8 feet, 2272 cubic feet. Next slide. So let's focus right in here. As a contractor, what do you need to know for ASHRAE 15.2 compliance? So we take all these 30 some odd slides that we just see, and what do you do with all this information? Let's condense it into the must know. The first bullet point, calculate the dispersal volume per area, per zone. Well, that's pretty easy. We know how to do that. That's length and width. That's area times the dispersal height. Again, keep in mind dispersal height can vary significantly depending upon the indoor unit type, whether it's ducted or ducted. Middle bullet point, we want to obtain the system charge, that is MS. And that's pretty easy. We'll talk a little bit more about how to do that. And what we have to calculate, the more challenging task here, is to calculate the max allowable charge for that smallest volume area. And that's what we'll use the table for. So next slide. If we take a look, zone 2, which was a ducted unit, my apology, I forgot to go back and look at that in the previous slide, but zone 2 had the smallest volume. So we can take the square footage and look in the left-hand column for the floor area. So 284, Leonard talked about interpolating. I would have to take my shoes off to do that kind of math. So let's just stick with what's easy. We can't go to 300 because that's greater than 284. So we'll default to the next lower, which is going to work against us potentially. So let's take a look. So 275 square feet, intersect that with the 8-foot column for the dispersal height. And that is under the green, that is without air circulation. So air circulation, again, just to clarify, is initiating fan operation of the indoor unit. That's it. This is, again, without outside air, So right away, we can see our max, our MX, our max allowable refrigerant charge for that smallest zone is 15.4 pounds. And what do we say the system charge is? 5.8 pounds. So we're, what, 2.5 times the amount, just right out of the box, even with the multi-zone system. So hopefully this can help melt some of that fear that we have about performing these calculations and what to do with this information. I have an asterisk on the bottom that says the factory charge equals the ASHRAE term of system charge known as MS. So no additional refrigerant in this example, but we'll take a look. Next slide. But let's just say we want to take this out to how much refrigerant charge can we have? What's our Mmax value with circulation? So all of our H series and J7S series ducted units will have or do have an LDS or a gas detection sensor that's built into the equipment. So what will happen is upon a leak event, if it detects it, it can trigger initiation of circulation, basically just turn the fan speed on and shut down the system, turn on the fan. So by diluting, so to speak, by being able to disperse that refrigerant charge through circulation, we can go with a higher amount. So now we can see, again, we're even what, 3 plus almost four times the max allowable refrigerant charge just with the system charge out of the box. Again, so we're well within compliance with virtually doing nothing. So this table is huge. This is an absolute key document that you'd like to have. Next slide. So we said it's good up to the factory charge of 5 pounds, 8 ounces. That is the, we can go, as you see, up to 164 feet of total liquid line length. So let's just say, for the sake of our argument, again, let's use a worst case scenario where you needed to max out the refrigerant lines to 230 feet. Again, this is collective liquid line length. So the difference between 230 and the pre-charge value of 164 is about 66 feet. So if we do 66 feet times the 0.21, that's the rate on the far right column. Well, our literature does the math for you. It tells us that it's 14 ounces. 14 ounces is the max that we can possibly add to this system. So if we take on the lower left now, the 2 bullet points, we take the factory charge of 5 pounds, 8 ounces, add the 14 ounces to it, we're just under 6.5 pounds, so 6 pounds, 6 ounces, and it's less than our max allowable refrigerant charge. So again, we're about half, if not less than half, of the max allowable charge, even with the full field charge adder for the liquid line. So again, you can see these, our systems don't have very much refrigerant, so the ASHRAE values are actually relatively conservative. Next slide. But wait, do we have any J-Series fans out here? So because J-Series is often used in residential, our upcoming J7S, our 2, 3, and 4 tons. So let's take the same scenario and let's just plug in now, substitute a 3-ton multi-zone with a 3-ton J7S. So the total refrigerant charge is quite a bit more. Now the factory charge is about the same, maybe a little bit more. However, because of the extended lines, we can have up to a whopping 7.3 pounds of added refrigerant that bumps us. And now again, that's if we maximize, absolutely maximize the allowable liquid line length in the field. That's about 13.2 pounds. So even at 13.2 pounds, we're still about 2 pounds less than the max allowable refrigerant charge. So even with J7S, we're going to be compliant. Next slide. So where can you get this information? Well, I want to focus your attention to the upper left underlined word that says planning. From my perspective, I think to map this out during the planning stage is critical, because you don't want to install a system and then come to find out you need some means of A2L mitigation afterwards that could potentially be an extra 4 digits to a project that your customer may not be happy about after the fact. So you want to do this during the planning phase. So where can you get this information? Right through our website, from our D&T manuals, our service manuals, installation manuals, and submittals. Can you get it off the nameplate of the unit? Yes. However, if you're doing this in the planning phase, you may not have the unit yet. So if you look here, as Leonard said, about 80% of our E-Series systems fall below that 4-pound threshold anyway. But with this particular single zone 3-ton unit, we see that we're at 3 pounds, 12 ounces. So we're only about 4 ounces short of hitting that 4-pound threshold. So if we take that 4 ounce amount until we hit 4 pounds, divided by the ounce per foot adder of 0.43, it comes to about 9 feet. So we know the pre-charge length is 66 feet. We add 9 feet to that. We come up to about 75 feet. So if the line set on the bottom bullet point there, bottom left. So if the line set's 75 feet or less, we're okay. But if we're greater than 70 feet, that's when we're 75 feet. That's when we're going to hit that 4-pound threshold or exceed it. And that's when the dispersal volume calcs will be required. But as you saw, really dispersal volume is not difficult once you know what to look for. Next slide. Are there any tools available from Fujitsu to help with the layout and compliance? Well, yes, we have the application guide that Leonard mentioned. And the reason I chose this particular little inset here is because understanding dispersal height and how it can be different between ducted and ductless systems is critical. So again, if you have a floor mount unit on the bottom left, your dispersal height may only be 2 feet. So that's going to significantly affect your dispersal volume, which is the value that we go by. We don't go by square footage alone, it's by volume. Next slide. What about Design Simulator? Those of you that are familiar with it, yes. And actually, this is a great tool. It covers all of our current production as well as our legacy H-series systems. It can be used for system selection and compatibility to make sure we don't have a mismatched system. Our product guides do have quick select tables. However, this drills down to a further level where we can do accessory selections, we can do capacity interpolation. For example, we know the unit puts out X amount of BTUs when it's 95 degrees out, but what if it's 115, or what if you're in a cooler climate? It will adjust those values for you automatically. It also provides the electrical connection diagrams, but I want to point out in the bottom center there where you see the red box, the total pipe length. So when you're inputting these values into Design Sim, it's going to tell you if you need additional refrigerant, and if so, how much based upon your line length. So you don't have to do any math that could be subject to error. Next slide. And this is key, the refrigerant piping diagram. I think this is a great tool to use for sales also. For example, if a customer says they're interested in you and your company, but you're $1,500 to $2,000 more than the competition, why should they go with you? Well, you can say, well, with new refrigerants, we have to be sure that we comply to the ASHRAE application standards, and we can be assured, we've got a permanent as-built record of the installation that can be used forevermore. So this is a great tool to use for making sure we have a compatible equipment selection, as well as making sure that we know what the exact refrigerant charge will be. And speaking of Design Simulator, on the bottom left, save the date. So we are going to have in about a month, we're going to have a webinar specific to our J series, and with the focus on Design Simulator use for R32 systems. And then about a month after that, Vikas, our commercial product manager, will cover the entire breadth of the R32 VRF line. Next slide. Another tool is, now this is great. This is really going to take everything that's in the ASHRAE 15 and 15.2 manuals, our application guide, and our application bulletin, and combine it into one very easy to use interactive, we call it the 3C, Charge Compliance Calculator. So this is coming soon. It'll be coming in about a month or so, and it's under final development and testing right now, but basically it's a user interactive table that allows you to enter the input fields such as your room lengths, your dispersal heights, total refrigerant charge, and it will tell you, depending upon your input, whether or not you're compliant with whichever standard it is that you select. So this is a great tool to have, and it has links to our documents as well. So this is a great tool that'll be coming soon. Next slide. How can automatic shutoff valves in a refrigerant circuit provide a benefit? So you've probably heard a lot about shutoff valves, and you're wondering what the heck are these things and where do I use them? First of all, let me mention that if you deal with H-series systems only, you don't have to worry about that. So the shutoff valves are exclusive to our VRF systems, our small VRF known as J-series, and of course larger. Why is that? Because, well, simply put, they're not needed for the smaller residential or H-series systems because the total refrigerant charge is just not that much. But in short, what it is think of it like a solenoid, except we use an EEV for complete isolation. So you see the two lines there. One connection is for the liquid, one is for the vapor, so inlet and outlet. So there's no phase change, there's no metering device. They are EEVs, but they're either going to be fully open or fully closed. So what the shutoff valve will do is basically now, in terms of your system charge, now we're going to interject a new term, which is MREL, or maximum releasable charge. So in other words, if there's a leak, we can contain that leak only to what's downstream of the shutoff valve, to include the indoor unit. Next slide. So what does that look like? So these are, I'm going to show 3 different examples here that are kind of extreme, one to the least, one to the most, and one in between. Don't worry about exactly how these are placed right now. I'm simply showing you how these can be used to effectively reduce the maximum releasable charge. So again, what are we doing? We're trying to determine what this maximum releasable charge is so we can compare it to the tables that we used before, so we see, based upon our dispersal volume, how much charge can we afford to lose in the space. So this is what's called a whole shutoff. In other words, if you look at the valve in the red circle, it will go ahead and isolate all of the indoor units collectively, as well as all of their liquid line. So if you notice on the lower right, we have the MS. That's a total system charge. Let's say it's given at 9.2 pounds. Now, factoring the complete, or should I say the cumulative charge between the 3/8 and 1/4 inch liquid lines, that's 1.2 pounds, 6.3 pounds for the indoor unit heat exchangers. And the shutoff valve itself, that comes up to about 7.5 pounds. So it is less, it's about 1.5 pounds less than total system charge. So it is most economical because here you're looking at basically just one shutoff valve that's wired to the outdoor unit. But the downside to that is your MREL values can be high because you're only really eliminating the outdoor unit and that short section of line between the outdoor unit and the shutoff valve. Next slide. Ding. Next slide, please.
I'm trying it long.
Oh.
There.
Oh, there we go. Okay. I know sometimes presentations have a conscience and they get mad if you try and force it. So, okay, so here's the here's the other extreme. This is a partial shutoff. Now, again, don't take this at face value that you have to put in a shutoff valve at every indoor unit. You don't. But just merely demonstrating what can be done if need be. Again, it's all a function of what's the maximum releasable charge that area can handle. So here it's least economical because now we have 5 shutoff valves. We're going to need some expansion kits which act as an interface for the shutoff valves, and we're going to need 3 gas sensor kits. Well, if there's 5 units, why do we only need 3? That's because the 2 ARUL units, those are ducted units, those come with the gas sensor already as an integral part of the unit. The upside of this is a significant MREL decrease. So before we saw that we had, what, I think it was about 7.5 pounds. Now we're less than half of that. So the largest of those zones is zone 2. So now we're only down to about 2.9 pounds. So a significant reduction in the maximum releasable charge. So again, if we were to have a leak at zone 2, for example, if that valve were to close, we're only going to lose 2.9 pounds of refrigerant. Next slide. So here's something in between, and this is what I'm going to cover in the webinar next month for J-Series, is what different strategies, how do you group indoor units, what different approaches are there to selection and placement of shutoff valves? Because there is a cost, so there is an increased cost compared to the whole shutoff, but it's not as much as a partial, so we call this a combined partial. So as you see, zone 1 and zone 2 are combined from a piping perspective, as are zone 3, zone 4, and then zone 5 is unto itself. So this is kind of in the middle. So it's a reduction compared to, or it's kind of right in the middle between the 2 extreme options, as I mentioned. Same system, same total system charge, but now our maximum releasable charge would be confined to zone 1 and zone 2. That's the largest value of 4.4 pounds. So we saw with the whole shutoff, it was 7.5. with the partial shutoff, I think it was 2.9. So again, we're kind of right in the middle here. But again, about a 50, actually more than 50% reduction compared to the total system charge. Next slide. Can third-party LDS sensors be used? Ooh, this is a good one. Well, it's not recommended. Why? Because the Fujitsu leak sensor that we offer, or going to offer rather, that connects on the case of H series as well as J series, if it's connecting to the indoor unit, it's done through a UART port. So it's a communicating device. It's not like most unitary sensors are intended for, or most generic sensors are used for unitary systems where we have your typical 24-volt connections that are interrupted, such as Y, W, G, things like that. Fourth bullet point, those of you, and actually probably all of you, are very familiar with our TTRX thermostat option. You can say, well, what if I use a TTRX, integrate that with the H series, and then just basically the control will provide an R to G override and turn on the fan. That may work. It's possible, but again, that's not something that we have tested, but it could work. And the bottom point is our native control. So those of you that are a little bit savvy on our additional external inputs and outputs, we could use an external input such as stop start or force stop that will turn the system off. However, when the system's off, it's just off, and we will not provide a circulation option. However, you may not need the circulation option, again, because go back to that first example that we had with the multi-zone system. It all depends upon the refrigerant charge compared to the dispersal volume. Next slide. Ooh, this is a good one, and we get asked this multiple times a week, which is why we released this application bulletin a few weeks ago. Can an existing line set be reused with an R32 system? Well, yes, obviously we'd prefer to see, as any manufacturer would, new lines installed with a system, but we know the reality sometimes economically that's not feasible, or in some cases, such as community housing, condominiums, things like that, they may not allow for a new line to be run external to the building. So what do you do? Well, we published this bulletin that has multiple answers. Primarily, we focus on the line set size, because traditionally we've never been allowed to really deviate from the sizes. We have to look at each one on a case-by-case basis. But this covers all of our H-series R32 products. We talk about the required line set and then some alternate line diameters. So we can go larger on our vapor lines up to, model dependent. We can typically go up to one increment larger on the liquid line. However, that's going to result in added charge, which means we cannot go as far as we could with the prescribed liquid line size. So it has to meet our requirements and, of course, that of local code. But as far as the national standard, 15.2 specifies that the piping shall be provided through a nail plate, for example, because obviously we don't want some other tradespeople, especially disgruntled, to come in and poke a hole in the line set. So in all seriousness, if you are doing an existing or doing a replacement project with existing lines, you may want to check, however possible, to make sure there are some nail plates in place. Next slide.
Thank you, Wayne. Yeah, thank you. That was very good examples. So just a couple of more slides here. This is the question we get. What can I do if I don't comply? Well, in general, it's either the room volume is too small or the charge is too big if you don't comply. And there are different ways to do that, whether it is a mini split system or even especially a BRF system. You can start the air circulation, first point there. You can perhaps remove or raise the suspended ceiling. We saw that on a slide earlier. You can perhaps relocate the fan coil and duct it to several rooms. You can install an RDS, because if you install an RDS and in a ducted system, and then you can have several rooms being used as the total floor space. But then that's when you need that RDS. They call it RDS or LDS. It's actually the same thing, just different name for it in the two standards, which is kind of strange. You can also install that permanent opening between connected room spaces. We saw earlier how that could be done, depending on which standard you're using. Add ventilation for dilution, that's going to help you with a few pounds. We saw it can be even more than a few pounds. And also increase the dispersal height by moving a unit in the unit higher up. Then we're going to increase the room volume. That's kind of what we do on the left there. On the right, we can decrease the refrigerant charge. We can perhaps, especially if it's a VRF system, divide it in multiple smaller systems. You might be able to replace or remove a coil, put in a mini split instead if you have a VRF system. You can install those safety shut-off valves that Wayne explained on the previous slide. Remove some piping, relocate piping. If you do that, you can perhaps shorten the piping, the total piping, and that's going to bring down the refrigerant charge and also the cost. Or there's also a possibility to use ducted zoning system for several zones. Then you can have several zones, but one unit, which means that the zoning itself will replace some of the piping that would be in the system otherwise. So this is a good slide for you. I'm going to leave it up for at least a minute or so. These are the QR codes for the documents that we talked about. On the first, you have the application guide that's available. You can go to that QR code. Then we have the application bulletin, the one with the tables. That is the second one. And then, of course, Fujitsu application library. You need access, log in there, but it's a lot of good practical information there, especially application related. And the Fujitsu Training Academy have really good classes for, especially now, how you handle R32, for example, but installation, some really good classes that we recommend. So those are the 4 QR codes that could be useful for you. Last slide, takeaway. And to try to summarize on one slide, the 15.2, standard 15.2 applies to residential stuff. Standard 15 is kind of for everything else. Standard 15 says that LDS can be required above 4 pounds, can be required, but that is if you needed to initiate operation of shut-off valves, air circulation, or ventilation for dilution. Otherwise, you don't need it. Also, a charge above 4 pounds doesn't need to mean that you need an LDS. Adding an LDS doesn't guarantee any compliance. Typically, it's the M max that make you comply with the standard. The maximum allowed refrigerant charge that you calculate to go into the table. And I also listed a good little note there, as we saw earlier. Any of the new systems in the 8 series, they have a factory charge that make them comply with a 100 square foot room and 7-foot dispersal height. Don't have to think about it. Can take any of those systems if you stay to the factory charge. Also, a reminder in the top right corner about the adoption process. ASHRAE Standard is one thing. The IMC is a step, or something similar is a step before it can go down to city and state code. And then we have those application guides that we discussed several times already. So that was the end of the presentation. We have almost 3 minutes left for questions. I think Wayne have visibility to the questions. We can try to answer those. If we don't have time, we're going to stop at 2 o'clock my time, but if we can't answer them, we will follow up individually for all the remaining questions. Your turn, Wayne.
Well, thank you, Leonard. And yeah, let's take a look here. So question, actually, we have 2 that are similar. What if you have a small room, say 8 by 10, how would you interpolate below 100 square foot rooms? Well, we can interpolate within the table. We cannot extrapolate beyond that. Now, I will say when the 3C charge calculator comes out, we will be able to enter in the exact values, and the calculation will be done for you. The math will be done for you. But what I would say to that is we would have to get a little creative here relative to the table, in that, as I mentioned, we are not going by square footage alone. We have to determine, first of all, what's connected and what's not connected in terms of spaces. But just, at face value, based upon what you're saying, so if we had an 80 square foot room, how do we do that? So what I would say is we would go back to the table. We can find, so if you knew your dispersal height, what we would need to do then is find a comparable dispersal volume to your to the 8x10 room, for example. So even though we may not have an entry that's exactly 8x10, if we find an equivalent dimension that has the same or close to or less than dispersal volume, that would work. We've got another question about part numbers and leak sensors, gas sensors. I do know they are coming and coming soon. I don't have the part numbers for those. I think we have a couple of sales folks on the line here. By all means, if you have that information, feel free to chime in and say. But I do know it's coming soon. I don't have the part numbers, unfortunately. And will a recording of this be posted on the Online Learning Academy? I know that a link will be published. I'll have to check with Brianna to see if they are going to be posted in the Online Learning Academy. Let's see, what other questions did we have? I think that was about it. Any more on your end, Leonard, that you can see?
No, I'm good. And it is 2 o'clock. We kept it in an hour. We answered some questions. Feel free to email Wayne or me or someone in the product group if you have additional questions. And then, as Wayne showed on one of his slides, in a month or so, we're going to have another similar webinar about the design simulator. And right after that, Vikas is going to talk about the R32 VRF system. So more is coming up, and we have actually more of these planned for the rest of the year. But expect, every other month at least, or even more often, we are going to do this. But thank you so much, and you let us know if you have any questions. Thank you.
Hey, Leonard, just one more quick point to the ones I wasn't able to answer exactly the questions as far as the part number and ETA. When we get that info, your questions are logged, so we know who sent the question, so we can respond to you individually with the answers to that. And that's it. Go ahead, Leonard.
No, that was it. Well, thank you, and we will talk to you guys again when we'll do that in, I think it's 4 or 5 weeks. Thank you.
Thank you, everyone.